So this is the continuation of the previous video. In the ideal state, this is the state when a RFID tag enters the magnetic field of the reader writer, and this is the state where the RFID is also powered or get the power from the magnetic field. So from this state the journey of RFID starts, and it's explained here that when the tag is in the ideal state, the reader writer has to send either REQA or the WPA. So for either of these two commands, the tag will get activated and it will return to the ready state. So when you read this paragraph, it's better you can also you keep referring to this diagram. Now from here, ideal state, so here the diagram says either a REQA or a WPA command will bring the tag to the ready one state. And if you look at this diagram, nowhere in the diagram it is possible to go back to the ideal state. So the only way the tag will come to ideal state is right from the no power state to the power state. So in all other states the tag will return back to the halt state. Now these states are very important during the anti-collision algorithm. The next is the ready one state. Now the ready one and ready two, these are all part of the anti-collision sequence. Now in the ready one state, the RFID tag returns the first part of its UID, and when the tag is selected in the ready one state, it returns the SAK byte equal to value 04, and this 04 means the UID is not complete yet. So we know that the Ultralight C has got 7 bytes in the UID. So in the ready one state, the first 3 bytes of the UID is returned. So it's very obvious that the complete UID is not recovered yet. So in that case, the SAK byte is set to 04. In the ready 2 state, so as you can see here, the tag from ready 1, after the first selection it moves to ready 2, and from ready 2 in the next select statement it comes to active state. So here there's an explanation here that says while in the ready 2 the second half of the UID is returned, and when the selection is done in the ready 2 state, the tag will move on to the active state. And you can see here the select command in cascade level 2, sometimes you might come across instead of the full word cascade level 2, you will see CL2. Now the select command in this ready 2 state will return the SAK value of 00. Now if the value is 00, it means the complete UID has been returned, and that means the tag is now active to receive or to process any commands. Now in the active state, we can do the read operation, the write operation, or you can also send an authenticate command to authenticate the tag. And you can also see there's a mention about, you keep seeing this word compatibility write. Now in Ultralight C, all write operations are 4 bytes, whereas if you compare this with the Mifare classic tag where the write operation is a 16 bytes operation. Now I rarely use this compatibility write. So however, if you are just not very sure where or why would somebody would like to use the compatibility write. Now here you are passing the 16 bytes, however only 4 bytes are returned. Now from the active state, if you send a halt command, the tag will return to the halt state. Now when the tag is in the halt state, there can be one more tag which is waiting in the idle state, and the idle and halt state combination of these are used to process more than one tag. Now here the halt state, what it mentions here is, on a successful halt command, the tag goes to halt state, and the only way you can bring back you can reuse this tag in the halt state is by sending the WUPA command, WPA. So using that, the tag that is in the halt, you can start reading. So this assume that we have got two tags. So one is idle, one is in halt. So I can select the halt tag. I can start processing that. The other tag will go to halt state. So this combination can be done. So if you want to learn how to copy from one tag to another tag without keep swapping the tags on the reader writer, so if you read the document on the PN532, there are some nice examples that shows how the two tags can be used automatically. And also keep in mind, ACR122 also uses a PN532. Okay. Now the authenticated state. See here, the tag behaves as a state machine, or it follows a state machine pattern of working, I would say. Now on a successful authentication command, the tag will be in the authenticated state, where it can read and write the protected memory. And there's a mention about here you can see that the authentication is performed using a 3DS authentication, which is described later. Now this is about for a developer this doesn't matter that much, because it says how the data integrity is maintained. So internally it generates a 16-bit CRC, and there is a parity bit, and all these things are related to how the byte is transferred. But from a programmer's point of view, we don't see the 16-bit CRC at all. So most of these CRCs are handled by the reader. So but internally if you look at the entire packet of data that is sent, as we say reader, and this is the tag. So any command we send, command and data we send, so it's finally cascaded with the CRC, and these CRC values are automatically calculated by the reader writer. So you don't see much often this CRC bit, but this is how the reader and the tag maintains the data integrity. So if somebody modifies, these bits are going in air. If somebody does have some instrument and try to modify these bits, obviously the tag will detect it, because the CRC will not match. So this is about I would say this is more of on a technical side. Okay, so it's just there's some information here as well, but from the developer's point of view we are not too much concerned with this information. The memory structure, we have seen this memory structure. Now this is the most important thing for a developer, and for programming this, it says it has got 48 pages. Certain important points I've highlighted. So when you buy this tag, the new tag will have all the bits set to 0. When you compare this with some other tags like SRX 4K or a Topaz, I suppose the default value of the tag is 1, and some of the contacts cards like SLE 5542, the default bit is 1. So this does matter for us, because we have to decide whether to write a 0 or a 1 depending on the initial value. Now every tag has got a 7-byte serial number, and it is all mentioned here that it says this 7-byte serial number cannot be modified, and this is all written during the time of manufacturing of this tag. And also some important information, it has got the BCC. So we keep seeing this BCC very often, and you just have to keep in mind, this is BCC means block check character, BCC. So these are programmed in the first 9 bytes of the memory. So we have seen this many times. So I'm going to show you just quickly to keep in sync with this the document. Now this is a structure of how the UID or serial number is stored. There are some nice information here as well. So here it shows, say for example, so we have got page 0, page 1, page 2. Now 3 pages are used to store the UID plus the log bytes. In the first page, the first 3 bytes, byte 0, 1 and 2 has got the 3 bytes of the serial number, and this is the check byte, and the check byte, this value is calculated like this way: CT followed by, these are all XOR operations, SN0, SN1, SN2, where CT is the value 88. So CT, again, we keep hearing this or seeing this in many documents. This is called as a cascade tag, and the remaining 4 bytes are stored in page 1. So you got 3 here and 4 here. You got all the 7 bytes stored, and there is also one more checksum, the BCC, and you can see that this BCC is calculated as SN3, 4, 5, 6. So SN3, SN4, SN5, SN6. Okay, this is the XOR operation, and it also mentions that this byte is internal, not used, and followed by the static log bytes. The static log bytes are stored here. So again, you cannot modify page 0, page 1, and even though we can modify the log bytes, I'm not sure whether you can modify this internal. I'm not very sure. So I think you cannot modify these 2 bytes also. So here it explains how the 2 bytes, the static log bytes are interpreted. Now every bit, so this is, for example, here this is called log byte 0 and log byte 1. The log byte 0 controls the locking of page 4, page 5, page 6, page 7, and the OTP. It also has got the block locking. And the log byte 1, which is the 3rd byte of page 2, controls the locking of the remaining pages. So here there's a nice explanation about what this BL means. Say the block locking means, when the block locking is 1, you cannot modify the value of 4 to 9. 4, 5, 6, 7, 8 and 9. You cannot modify any of these log bits. So this is like a blocking the lock bits. When the BL1510 is set to 1, you cannot change the lock bits, values of lock bits from 10 to 15. Obviously, this bit here, BL50, controls the locking of OTP. Assume that you do not want anybody to lock the OTP. What you can do is you can just store a 1 here, and nobody can lock after that. It also says about, so the other thing here is the lock bytes are irreversible. So once you lock a page, so you cannot unlock it. That's what highlighted here. And the default value for the static log bytes are 0, 0. And here it explains whatever we discussed and explained in this table. Now because this Ultralight C has got more than 16 pages, So there are two more log bytes called log byte 2, log byte 3, which is if you go back to the diagram. So if you work on this tag a lot, so you can take a print and stick it on the wall. Now here, these two more log bytes, which are in page number 28, and you know that these two bytes are not used. Likewise, the 16-bit counter in the page 29, so the 2 bytes are not used. So here probably I didn't mention about this table. So this table says there are, from page number 427, you got user memory where you can read and write, followed by the log bytes, followed by the 16-bit counter, followed by the 2 configuration pages, followed by the authentication key, the 4 pages of authentication key. Now here the explanation about how the additional log bytes 2 and 3 are coded. So here is exactly the structure is similar to the static log. Every bit controls 4 pages here. Say if you set the bit number 7 of this byte, this is going to lock page 36 to 39. Like that. Likewise, if you set the bit number 6, it's going to lock 30 to 35. So similarly, just like there were block locking in static logs, here also you find the BL bits. Say for example this bit. This says the block locking for page 29 to 39. So the page 29, not very sure where is page 29. So I'm sure this from 28 to 39. So let us see what is page 29. So it's a 16-bit counter. I'm not very sure why it is, because there is also a block locking for the counter here. I'm not very sure why the document says 29 to 39. So probably I think this should be 28 to, look at that, by just putting a 1 in this bit position, you cannot modify these 3 bits at all. In other words, you cannot change the locking of 28 to 39 page. So likewise, you can also lock, see all the locking, you can also lock the page 16 to 27 here. So this block locking will prevent any further changes to these 3 bits. You also got the block locking for the key. The keys are stored here, the page 47, 44 to 47, and you got the locking of auth 1, the configuration 1, locking of configuration 2, locking of the counter. Every piece of information in that card can be locked, and similarly every pages or feature you can also block from locking. So next is the OTP bytes. This is in page number 3. This is like a 32-bit, like a 32-bit value which you can set it to 1, and this is like a one-time setting, and this is this feature is most commonly used in a single day ticket or a monthly pass, where each bit can be set as a daily ticket. And the example shows here, but keep in mind, when the bit is set to 1, you cannot change it to 0. This is a irreversible set, so there are 32 bits. You can use this for 32 entry ticket or 32 ticks, so on. The default value is all zeros. The next is, next most important thing is the authentication, and this is of this feature why the ultralight tags are very popular. You can protect or password protect the tag using authentication based on the 3DS algorithm. So I'm going to show you, how the 3DS works by taking a simple and non-technical example. So this is 3DS authentication in a very simple words. Take for example, two entities wants to make sure that each have the same secret key without showing the key itself. Now this is how the 3DS authentication works. Now here the two entities are, one of them is the reader, the other one is the tag. So I've got a few screenshots here of my scribbled on the paper. So A and B are the two entities. Now B wants to transfer some data to A. Now what B does is, take for example, it wants to transfer the number 1079 to A. So B first encrypts the data and it gets the encrypted value of 1079, which is here I've called as XYZ. So XYZ is transferred to A. A will decrypt it. So when it's decrypted, assume that the decryption is a success. It gets 1079. So A will again encrypt it back to get encrypted 1079. I'm going to call this as MNP. And this MNP is passed back to A. Sorry, back to B. Now what B does is, it will decrypt MNP and it gets 1079. Now this matches B. Now from the B's point of view, B sent 1079 and it got back 1079. So now B knows A has the secret key, which is same as B. Now B has authenticated A, or that. So B has trusted A now. But what about A? How does A know B also has got a secret key, the same secret key? Now what we have seen here is just the first half of that authentication process. The same process will repeat in A as well. Now here assume that A will send its own number. Assume that A has got 5946. It encrypts, it gets XYZ. This is passed on to B. B will decrypt it and it will again encrypt. See, when the decrypt encrypt happens, it will be using a key that is stored inside B. Same thing as the key stored inside A. So there's no key is traversed in the air. Now this 5946 is encrypted to get PQR. The PQR sent back to A. A will decrypt and check. It sees 5946, which matches the original value of A. Now A knows B has a secret key. So both A and B are 100% sure they are talking to people with the same secret key. Now this is a bit of a lengthy process. In the reality, okay, the previous two steps can be simplified, and this is how it can be done. So B, take for example the same number 1079. So B does the encrypt, it sends XYZ to A. A will decrypt it, it gets 1079, and A will also generate a number 5946, and these two numbers are encrypted to get MNP XYZ, something like that. It's sent passed on to B. B decrypts, it will get back 5946 1079. B compares 1079 with itself, this part, okay, it compares this part is compared. Now this matches this. Now B is 100% sure A has got the same secret key. Now what B does is, it will encrypt the 5946. It sends it MNP, it's encrypted value, sends it back to A. Now A will decrypt this MNP, gets 5946, matches. Now both A and B knows that each one of them have got the same key and they trust, and this is called as a mutual authentication. A has authenticated with B and B has authenticated with A. Now this is how the 3DS authentication works in the Ultralight C tag. Now back to the documentation. Now this is the best explanation about how the 3DS authentication works, and this is called as a 2-key 3DS encryption, and some of the important words I've highlighted, and this uses what is called as a CBC mode. If you are programming this in a programming language like a Java, C# or any .NET language, you have to look for the CBC mode. There are other modes like ECB mode, and I think ECB I'm very familiar, so you cannot use that. But there are some nice documentation internet. Search for the CBC mode, and you'll find some nice articles. And I have read there are some easy to understand articles. So some of the important things here are the initial value. This is more technical. This speaks about the algorithm. It says initial value or the first encryption must be 0. You have to understand all these things, if you are programming 3DS key. Now what we discussed in the previous slides is explained here. So it's always the reader that challenges the pick. It says it sends the authenticate, and here the explanation is exactly what I mentioned before. The pick sends a number, and the PCD will decrypt it and sends its own number back to the pick. Here you can see that the RNDA is from the PCD side and RNDB is from the pick side, and this step here verifies that RNDB is matched. Then it encrypts and sends back RNDA, and this step here will again decrypt and it will match the RNDA. Now both the PCD and the pick will match, and they know that both of them have got the same secret key. So in any one of these steps, if there is no match, then that is recognized as an error. And in the block diagram, when the authentication fails, it returns back to the halt state or idle state, whichever the state the pick started from. There's a nice example here. I don't want to go through the example. I'm going to show you a couple of videos I've done which have explained everything step by step in detail. And some of the important points here are, it says in the key the parity bit are not checked. So we say that it has got 16 bytes. So however, the 1 bit of every byte is not used as a key. So there are some document that explains how you can use those bits as a version of the keys, and this is a nice example here. So when you write a program, you can take this as an example and compare the intermediate values. Is exactly what I have done. If you go to YouTube and type the Ultralight 3DS, you get all these listings are my videos, and these are done probably now. You can see some of them are done 2 years ago, but I've taken exactly the same example we saw in the document, and I explained everything in detail step by step. So probably now I also got a playlist here. So you can see that the playlist is understanding 3DS in Mifare Ultralight C. Now there are 5 videos. I explained everything in detail, and altogether you can see it has got around 50 minutes of video. They're worth watching. So I would advise you to see these videos to understand the 3DS better. So in this section you will see how the 3DS keys are stored in the memory, and it's not very straightforward, because say for example, if the 2 keys are this and that, the way it is stored in the memory is you have to consider this the last byte as the lowest byte. The lowest byte is stored here, and even when you this is a very nice example here. So assume that I want to store my keys are this and this. So because there are 16 bytes, we will end up using a 4 write command. In the first write command, you are passing the lower bytes, so 7 6 5 4 in this order, followed by 3 2 1 0, and followed by this F E and so on. And if you look at here, the way the data is stored is the 7 is stored first and followed by 6 and so on. Okay. And also there are some important points here. The memory pages holding authentication key can never be read. And also, so I mentioned in my previous videos, you should give more like you're reading this the remark bits. There are some information as well. It says any reprogrammed authentication key is only valid for authentication after RF reset. So if you change the key, you cannot authenticate immediately. So assume that you are writing, you are changing the key and you want to verify the key. You cannot do the verification immediately after write. You have to reactivate, take out the key out of the field and put it back. I think I missed some more remarks on the top that's related to the locks. And yeah, there's some interesting bit here. The configuration returned in the log bytes is valid upon the next REQA WPA. So this also means the same thing. If you lock a page, so it will be effective only after the next activation command.